Okay. A buffer solution contains, a buffer. So when we say buffer, we mean a buffer solution. A buffer contains 0.30 molar ammonia, NH3, wow, and 0.45 molar NH4Cl, ammonium chloride. What is the pH? What is the pH? And the Kb for ammonia is 1.8 times 10 to the negative 5. Now notice, in this case, we have a buffer solution that's not made with a weak acid and the salt of its conjugate base. It's made with a weak base, ammonia, and the salt of its conjugate acid, ammonium chloride, the conjugate acid being ammonium, NH4+. So now it's slightly reversed. And notice, this is Kb, not Ka. When we use the Henderson-Hasselbalch equation, here's another reason why I don't like using it, because in this situation, you can't use it directly. You actually have to calculate the Ka and then use it. The Henderson-Hasselbalch equation is pH equals pKa plus the log of the base over the acid. It's not a problem, it's just an extra step, but the idea is how the way we did it initially with the ice chart and everything, you can always just do it. That never changes. That's the nice thing about the sort of what I call the more rigorous method. But that's not a problem. We can go ahead and, so we'll use the Henderson-Hasselbalch equation, but again, it has to be Ka. So we know that there is a relationship between Ka. That's Ka, Kb equals Kw, which means that Ka is equal to Kw over Kb. In this case, it's going to be 1.0 times 10 to the negative 14. That is the equilibrium dissociation constant for water divided by the Kb here, which is 1.8 times 10 to the negative 5. And we end up with a number which is 5.6 times 10 to the negative 10. Okay. Now we write down the Henderson-Hasselbalch equation equals pKa plus the log of base over acid. In this case, the base is NH3. That is your weak base. Its conjugate acid is ammonium. So remember, base over acid. Let me just write that here. This is the base on top, and this is the acid on the bottom. That's the Henderson-Hasselbalch equation. Okay, so that means it equals, the pKa is the negative log of the Ka, which we just found, 5.6 times 10 to the negative 10, plus the logarithm of the ammonia concentration, which is 0.30 molar, over the NH4, over the acid concentration. NH4 is the conjugate acid. This is fully soluble, which means that 0.45 moles per liter produces 0.45 moles per liter of ammonium, equals 9.25 plus a negative 0.18 for a final answer of 9.07. There you go. That's it. Using the Henderson-Hasselbalch equation, you ended up, the only thing you have to be careful of is, of course, you have to work with Ka, because the Henderson-Hasselbalch equation requires that you work with Ka. So if you're dealing with a buffer solution that has a weak base and the salt of its conjugate acid, you're going to be given Kb for that weak base. You just need to calculate the Ka, put it in there, and you'll get your final answer. Now, of course, you could have done this with an ice chart and Kb. In fact, I'm going to do it real quickly just so you see how you actually could have done this. So we could have done the following. We could have said, okay, what are our major species? Well, our major species are ammonia, water, ammonium, and chloride. Well, what's going to dominate the equilibrium? What's going to dominate the equilibrium is that. Because again, the Kb for H2O, which, well, for H2O we're talking about 1.0 times 10 to the negative 14. This is 1.8 times 10 to the negative 5. It's so much bigger than that, so these are going to dominate. And here's what happens. You get NH3 plus HOH. It's going to be in equilibrium with NH4 plus OH minus. We're going to end up with a basic solution because we're creating hydroxide. Well, our initial, our change, and our equilibrium. Our initial ammonia concentration was 0.30. Water doesn't matter. 0 for hydroxide, nothing is there. Our initial ammonium concentration was 0.45 molar, right? That's exactly it. And now again, the change. This is going to diminish. Water doesn't matter. This is going to show up. This is going to show up. We're going to have 0.30 minus x. This doesn't matter. This is going to be 0.45 plus x, and this is plus x. Well, we have Kb is equal to the OH minus concentration times the NH4 plus concentration over the NH3 concentration. You have 1.8 times 10 to the negative 5 is equal to x times 0.45 plus x over 0.30 minus x. And again, x is going to be so small because of this common ion effect that you can pretty much ignore it. It's going to be x times 0.45 divided by 0.3, and here we get x equal to an OH. Now, this is where you have to be careful. We're looking for the H plus. We have the OH minus, well, we have to do that first. Equals 1.2 times 10 to the negative 5, which gives me a pOH of 4.92, which gives me a pH is equal to 14.00 minus 4.92. Let me make sure that minus sign is legible. 4.92, and we get a pH of 9.08, which matches our pH that we got doing the Henderson-Hasselbalch equation. For that one, we got 9.07, but again, 9.07, 9.08, you ended up in the same place. This is sort of the rigorous procedure. You have the Henderson-Hasselbalch equation, which is just a rearrangement of this for acids, because Henderson-Hasselbalch requires Ka. pH equals pKa plus log of base over acid. That's it. Thank you for joining us here at Educator.com for AP Chemistry. We have one more lesson of buffering solutions to discuss. We'll see you next time. Take care. Bye-bye.